All of our communications essentially depend on the transmission of signals across distances. Whether it is speech traveling through the air or a radio broadcast reaching a receiver, energy and information are moving from one point to another. We call these propagating patterns waves. But the strange thing about a wave is that the pattern moves without any actual physical transfer of the matter itself. The medium stays put, only the disturbance travels. Physics divides these disturbances into three broad categories. Electromagnetic waves, like light and X-rays, can travel through the vacuum of space. Matter waves are a quantum mechanical phenomenon associated with particles like protons and neutrons, and mechanical waves require a physical medium to travel through. While matter waves are conceptually abstract, they have highly practical applications. By harnessing the wave properties of electrons, devices like the electron microscope allow us to resolve structures far too small to be seen with standard visible light. But let's look closer at mechanical waves. If you drop a pebble into a pond, the water surface gets disturbed. The ripples expand outward in rapid circles. Yet, if you place a few pieces of cork on that surface, they merely bob up and down. The water mass is not flowing outward with the rings. Instead, elastic forces are binding the water molecules together, allowing the motion of one to affect the next. To understand the mechanics of a wave, we have to stop watching where the overall pattern is going and start looking at how the individual particles inside the medium are behaving. We can map this behavior by looking at a stretched string. Let's designate the direction the wave travels, its scoreward propagation, as the x-axis. If you give one end of that string a sharp jerk, a pulse travels down the line. The individual elements of the string do not move forward along the x-axis. They oscillate strictly up and down along the y-axis. If that motion is continuous and periodic, you generate a harmonic sinusoidal wave. Because particles move at a 90-degree angle to the propagation, we call this a transverse wave. This perpendicular motion has strict material requirements. As the wave propagates, it subjects the medium to a shearing strain, which is a force that pulls neighboring particles sideways. Transverse waves can only propagate in media that can sustain shearing stress. Because of this, transverse waves are mostly limited to solids and strings. Fluids, like liquid water or the air around us, have no shear modulus. If you pull an air molecule sideways, it doesn't drag its neighbor along with it. A transverse wave relies entirely on that rigid, perpendicular geometry to pass energy down the line. Sound waves traveling through the air operate under a completely different set of rules. We can't see the air moving like we can see a string vibrating, but we can visualize the mechanics. Imagine a long pipe filled with air, with a piston at one end. A sudden push forward and pull backward of that piston disturbs the air molecules immediately next to it. This creates condensations, tightly packed air, and rarefactions of lower density. As molecules push outward, the disturbance travels down the pipe. Notice the geometry. Molecules oscillate forward and backward, parallel to the wave's travel. This defines a longitudinal wave. While fluids cannot sustain the shearing forces needed for transverse waves, all elastic media, solids, liquids, and gases, can sustain compressive strain. They can all be squeezed. That makes longitudinal waves incredibly versatile. In fact, some materials are structurally complex enough to handle both. If you strike a steel bar, both transverse and longitudinal waves will propagate through the metal at different speeds. By shunting density and pressure in parallel lines, longitudinal waves allow energy to move effectively through the very air we breathe. It is easy to look at the surface of a lake and assume water waves are purely transverse. They look exactly like the ripples on a vibrating string, but water waves are actually a hybrid. The particles in a water wave undergo a complex motion. They move up and down, which is a transverse motion, but they also move back and forth, which is a longitudinal motion. Combined, the particles are actually tracing perfect circles. Two different restoring forces create this effect. Short ripples, called capillary waves, are produced by the surface tension of the water. Larger gravity waves are produced by the pull of Earth's gravity, trying to keep the water surface at its lowest possible level. And this circular oscillation isn't confined to the surface. The particle motion extends downward, with the circles shrinking in amplitude the closer you get to the ocean floor. Whether rippling through the ocean, traveling down a steel beam, or carrying voices across rooms, Its physical identity always comes back to a single relationship: the direction of the particle's motion compared to the direction of the wave's propagation. We separate these behaviors into perpendicular and parallel categories to study them. But out in the physical universe, these forces are frequently dancing together in unison.